The most important thing you're going to need to remember from this video about applications of logarithms is basically anytime you have a variable in an exponent, the only way you're going to be able to solve for it is using logarithms. So that's the power of logarithms, solving for a variable that's up in the exponent when you really can't reach it. Now let me give you a scenario where we're going to use it. Consider the general interest formula for multiple compounding. Now this involves your money at the bank.
It's mine, you understand? Mine, all mine.
A stands for the accrued amount that you get, the total amount accrued, principal and interest over the years, if you've invested P amount of principal. Okay, that's the amount you put in originally. R is the interest rate. T is the amount of time that you invested in years, and N is the number of periods per year. For instance, quarterly, N would be 4, or monthly, N would be 12, etc. Now before you get nervous, let's answer a question using this formula without using logarithms.
Now what am I gonna do?
Consider how much would you, the investor, accrue, how much money would be in your account if you invested $500 at an interest rate of 7% for 4 years. You kept it in there for 4 years when the interest is, as typically it is, compounded monthly. Well, let's put the numbers in. Our principal is 500, as you can see. 0.07 is 7% for the interest, and the magic number for monthly is 12, and the time, T if you would, is 4. Now all we have to do is use this formula. Basically, I would put this into a calculator, make no mistake, okay, because there's no solving. And this is what you'd have to type. Please note that you'd have to put the exponent 12 times 4 in its own set of parentheses. Anytime you have an exponent, it has to be in parentheses.
Oh, it didn't work.
Okay, be careful with parentheses or you'll get an answer, it just won't be right.
Show me the money!
And the answer in this case is quite logical. After 4 years, $500 will have turned into $661.03. Let me do this one more time, just to make sure you're familiar with this formula. Okay, let's start off again. How much would an investor, that be you, accrue? How much would they have in their bank account throwing down $3,000 at an interest rate of 10%? That's a hefty interest rate, but for 5 years, so it's in the bank for 5 years, when the interest is compounded quarterly. Well, that means the magic number is 4. So putting in all our numbers, we're going to have a 3,000 for principal, 10% or 0.10 for interest rate, and 4 for the N, and of course 5 for the time in years. And if we put this into that calculator, it should basically look like this. Once again, I warn you, make sure you put the exponent in parentheses. Okay? And you got a lot of free money there. Remember, you started off with 3,000. Now you had a high interest rate. You waited 5 years. But if you think about it, your 3,000 turned into 4,900 something. So basically you got $1,900 of free money. That's what I call it anyway. Okay, so that's how this formula works.
Excuse me, Professor Brainiac.
Okay, let's get back to what are we going to use the logarithms for? Well, let's look at the same formula, but we're kind of going to ask a different question.
This is a pickle, George. This is a pickle.
Here we go. How long, now we're asking for time, how long would it take you, an investor, to double your investment of $600 if you had an interest rate of 12% and the interest is compounded monthly? Well, let's put the numbers in to our old buddy, the formula. We know we're going to put $600 in originally. Where did the $1,200 come from? Well, it said it doubled it, so I doubled it. So apparently that's what my accrued would be, obviously, if I doubled $600. I put 12% in for the interest rate and 12 in for the N, because it's compounded monthly. Now I'm supposed to find the T. I want to know how long to do this. Well, that T is going to be a problem because he's up in the exponent. Well, let's start solving. I know I can get rid of the 600 by dividing both sides. Okay, and 1200 divided by 600 is 2. And I think I can do what's in parentheses. Okay, and add 1 and 0.01. But I still have a problem here. I've got 12t up in the exponent. Kind of can't reach him, can I? What would you do to both sides? Well, I don't know if you remember, but when we have something of this form, here's where you're going to use the logs. Note that it has the variable we're looking for in the exponent. So that's when I've got to get you used to taking the log of both sides. Now, what's the advantage of that? Remember the properties of logs? It's going to allow us to take that 12t down in front where we can do something about it. Okay? Now, who's keeping t from being alone? Well, the 12, who's multiplying, and the log of 1.01, who's also multiplying. So what I could do is divide by them. And I'll get, I can put that into my calculator, the log of 2 divided by the log of 1.01. Now all I have to do is figure out what that number is, and then divide both sides by 12. And 70 divided by 12 is 5.83. Now the question asked how long, so the answer is 5.83 years. Pretty cool. Couldn't have done it without logarithms. Now in banking, other than the amount you've invested, the time is about the only thing you have any power over. You have no power over the interest rate. Certainly the formula controls the accrued. So, you know, these are the kind of questions we'll be asking. How much should I invest, or how much time should I invest it for? Let's try another one. How long would it take an investor to earn $200 of interest? It's asked in a different way here. To earn $200 of interest with an investment of $1,500, that's the principal, at an interest rate of 10%, when the interest rate is compounded semi-annually. That's twice a year. Well, once again, let's use this formula and put in the numbers. I put in the 1,500 for the principal. The 1,700 came from adding 200 to the 1,500 because I earned 200 of interest. Recall that the accrued is principal plus interest. And then, as you can see, your blue 10% and your 2 for the N. And what I don't know is time. So let's divide first to get rid of the 1,500. And I'll reduce that fraction. Okay, now I'm going to leave it like this. I'll show you why in a second. What I mean is I'm not going to divide 15 into 17 just yet. Okay, pay attention. Now, I'm going to do what's in parentheses. I can do that with my calculator. 1 plus 0.10 divided by 2 is 1.05. Now, since I'm looking for something in the exponent, the t, that red t, I can't get to it unless I use the logs. Okay, remember what the log, the property of logarithms, allows me to do. It allows me to bring that 2t down in front where I can do something about it. Now, I've got the log of 17/15 on the left, and on the right, I've got to get t alone getting rid of, who's keeping it from being alone, is the 2, the brown 2, and the log of 1.05. And both of them are multiplying. So I'm going to divide both sides by, I'll do it in one step. That'll get rid of the 2, and it'll get rid of the log of 1.05 and leave me with t. Won't it? Now I've purposely not done any calculations on the left in all that nightmare, because what I want you to get used to, if you're going to use your calculator, every time you hit enter on your calculator, it gives you an estimate. So if you have to hit enter 4 times, you're going to be off, well, 4 times as much. So we want to try and do our calculations by only hitting enter once. So let's try and do this in one step on the calculator, so not to truncate or lose accuracy in the calculator. And the answer you get is 1.28 years. It's going to be a tough one to put into the calculator, but what you need to know is always put the whole numerator in parentheses, the whole denominator in parentheses. Any logarithms should have their own set of parentheses. And finally, any exponent should have his own set of parentheses. That's 4 things. And when you're done, when you're about to hit enter, make sure you have an even number of parentheses, because every beginning parenthesis should have an ending parenthesis. That's a numerator should have its own parentheses, a denominator should have its own parentheses, any logarithm should have its set of parentheses, and any exponent should have its set of parentheses. That's going to be the tough part in this case.
Transfer of data is complete.
Okay, give it a go. Remember, anytime you're solving for something in an exponent, you're going to be somewhere taking the log of both sides.